In this video, I want to introduce you to the Wilcoxon rank sum test, a rank-based test for two independent samples. You may recall that we had a Wilcoxon one-sample test. This is the same Wilcoxon who developed this two-sample test. In the previous video, we looked at the Fisher-Pitman type randomization test for two independent samples. We'll now follow the same line of reasoning with ranks of scores as a means of arriving at the Wilcoxon rank sum test. The packages required to follow along with this presentation are nplearn and coin. We have random samples from two populations. We might take a sample from each of two existing independent populations to compare them. More commonly, we may have one existing population and we draw a sample from that, randomize members of that sample to two conditions, one to represent the existing population and another to represent a potential population, a population of individuals that could potentially obtain the treatment. We have independent observations within each sample. With identical shapes and a quantitative response measure, the null hypothesis is that the median of two conditions are equal. I'm using here sub p sub r, taking off from the last video, in which we had a prosodic reading condition and a repeated reading condition. I'm going to use that same example in this video. The alternative hypothesis is that the median of the prosodic condition will be less than the median of the repeated readings condition because we're looking at errors, and we think that prosodic reading will reduce the number of errors. Without shape identity, or this is something new with the rank-based method, if we have an ordinal response measure, we could use these two competing hypotheses. The null hypothesis is that the probability of obtaining a score from the prosodic condition that is less than a score from the repeated reading conditions is equal to 1/2. There's an equal probability that the smaller score will come from either condition. But the alternative is that we will have a higher probability that we obtain smaller numbers of errors from the prosodic condition than we do from the repeated reading condition. The difference between the test statistic in this method and the test statistic we used in the Fisher-Pitman method is in that method, we summed up the scores of the smallest group. In this method, we rank all of the scores in both conditions first and then sum up the rank of the scores that are in the smallest group. That then leads to T, our test statistic. We look at all the possibility of combinations of ranks in the two conditions and calculate T for each combination, sort those, and then calculate the cumulative probability. I've done that here. So notice that in addition to loading in the prosodic scores, as I've done here, and loading in the repeated scores, as I've done here, I then took and combined these in order to rank. Once I had those ranks, then I could create my exact two-sample distribution based upon those ranks, looking at the ranks in the group with the smallest number, that is sample size 4. And you see here that our smallest value of T that we can obtain is 10. And if we move down to the bottom of this, we'll see that the largest value we can obtain is 30. So the sum of the ranks can go anywhere from 10, and think about that a moment. If you have a sample size of 4, then the smallest number of ranks would be 1, 2, 3, 4. Add 1, 2, 3, 4, and you get 10. That's the smallest value that our T statistic could be. We have equal probability for each one of these combinations. Some of the combinations, such as 12 appears twice, 13 appears 3 times. Some combinations appear more than 1 time. And so the probability of getting that particular T value is going to be greater than when it only happens one possible way. We have cumulative probabilities from the bottom up and cumulative probabilities from the top down, we're going to use from the bottom up because our hypothesis is that the median for the prosodic condition will be less than the median for the repeated reading condition. Here's our observed test statistic, adding up the scores and the ranks of those scores with the smallest number of values, that is 4, the prosodic condition. We have a sum of ranks that total up to 11. So if we go back here and look for 11, here it is, and it's a lower sided test. So we got 0.0159. If you watched the last video, you'll recognize that that is the same thing we got in that last video. That's just happenstance. That's not always the case that we get the same p-value. Otherwise, there would be little reason to do this method instead of the other one. We will often get different p-statistics. We just happen to get the same one here. Here are some R functions. There is a function called Wilcox.test, and that is built into base R. So the Wilcox.test is done like this. We enter in the two groups, prosodic and repeated reading, set the alternative hypothesis, and ask for an exact test. The problem is that we will not get exact values with ties. Here we did get the exact value of 0.016 because we did not have ties. But if we do have ties, we can turn to the coin package. So I typically use the function out of the coin package regardless because it has more options available to us, including the possibility of ties, in which case we'll use mid-ranks. I've talked about mid-ranks in previous videos. So here we have now the condition set up as a factor, and then we enter in score as a function of condition, and setting the other arguments very much like we did in the base R function. The alternative is less, the distribution's exact, and we ended up with 0.016. I'll also point out that this particular function has an exact method available, a Monte Carlo approximate method available, and an asymptotic method available in case we get very large sample sizes. Let's compare this test to both the t-test and the Fisher-Pitman type 2 sample test. This test is based on ranks, so it is asymptotically more powerful for heavy-tailed distributions. This test is based on ranks, so it is asymptotically less powerful for a normal distribution. The Fisher-Pitman and the t-test have the same power as one another, but that power will be less than the rank-based test if there are heavy-tailed distributions, that is, higher than normal kurtosis. And if we have a normal distribution, they will be more powerful than this Wilcoxon rank sum test. This test is less computationally intensive. Why is that? If you don't have ties, then we know for the sample size what all the ranks are going to be. And we can actually create formulas to calculate the possibilities for ranks without doing every possible combination. A special case of this test can be used with ordinal data. That was not the case with the Fisher-Pitman type test and the t-test. But with the rank test, if we have ordinal data, we can use the second form of the null and alternative hypotheses to conduct a test. If we have a large sample, by the central limit theorem, T, the sum of the ranks of the smallest sample, or one of the samples, traditionally we use the smallest, approaches a normal distribution. And importantly, we know the mean and standard deviation of that distribution. The mean is going to be N1, the smallest sampled sample size, times N, the total sample size plus 1, that product divided by 2. That will be the mean. The standard deviation is the square root of the product of the two sample sizes times the total sample size plus 1, all that quantity divided by 12. So we could put in that mean and that standard deviation that is based just on sample sizes. That's why this is a non-parametric test. We don't actually have to know those parameters. We only need to know the sample sizes, and we can use the tails of the normal distribution with those parameters to test the null hypothesis.